Dr. Fred, you're on mute. We can't hear you.
Thank you. I can hear you though. Thank you. I was still muted. You're supposed to unmute automatically. Apparently, it is not. Okay. Well, welcome back. What I want to do, point number one is one. Don't forget today's exam. You have the 10 p.m. chapter 7 through 9. 21 questions. Okay, similar format as before. 75 minutes. So give yourself plenty of time if you haven't done it yet. I will go over that activity simply because I got a lot of them done. I got quite a number of them, but not all. And so what I want to do is go over them. There was some confusion about the activity and naming the compounds. For example, the activity said, record yourself in your face. Well, okay, that's one word, one thing there. I didn't write this. This is done by the department. If you don't want to, if you'd send a recording of your voice, that's sufficient. There are some people that don't want to record their face for multiple reasons. That's fine. But as long as I can hear you, I'm good with that. Okay. Anyway, this is in great detail on how to name these two compounds, SR parentheses OH in parentheses subscript 2 and FE parentheses OH in parentheses subscript 3. Okay. Well, first one, SR strontium. Okay. And OH, obviously, hopefully, if you don't know, it is, because the thing is that you got a parentheses and net. When you see a parentheses, go to your polyatomic ion table because that's what you're working with. Look up the OH, you'll find it to be the hydroxide. So be familiar with the hydroxide. It'll be coming here, it'll show up many times. So it's a base. Okay, so this one is called strontium hydroxide. Now, we don't use Roman numerals because strontium is part of the 16. Remember those 16 elements or metals that we know their oxidation state of 100%. SR is in group 2. And so therefore, all we got to do is give it the name and we're done. And then the hydroxide, strontium hydroxide. No prefixes for either one. Why? Because both of these are ionic compounds. We have metal and non-metal. So both of them are ionic compounds. Now, with respect to the next one, the Fe, which is iron, okay? Iron is not part of the 16. It is a variable, has a variable oxidation. There are two types. It could be iron plus 2, could be iron plus 3. So what we got to do with this example, we have to figure out which iron we're working with. But what do we know? As I stated before, the total number of cations plus the total number of anions would equal 0. Those are three unknowns in that equation. You're always going to know two of those three unknowns. Here, the charge for the whole molecule is 0. So that's one unknown. The next one you do know is the OH. OH has a -1, okay? That polyatomic ion has an overall -1 charge. There are 3 of them, 3 hydroxyl ions. So it's a total of a -3 charge due to the hydroxyl. What that implies is iron must be a +2. +2, -3 equals 0, okay? Therefore, what you're working with here is iron, Roman numeral 3 hydroxide. We use the Roman numerals only for those metals that have a variable oxidation number, which means those are those metals other than the 16, okay? Because this one has a +3. So the next question, what type of compounds are they? I mentioned at the beginning, both of them are ionic compounds. It's a combination of metal and non-metal combo. The OH, the hydroxide, is the non-metal. The charges, I just talked about that. SR is in group 2, 2A. 2 valence electrons. It's a metal. All metals lose electrons. Therefore, it will end up with a +2 charge. And iron, the iron, we had to calculate that because we didn't know it's a variable oxidation. We calculated it to have a +3 charge. Okay. And it says, how are the nomenclature rules different for these two compounds? Again, SR has an exact oxidation number and therefore does not require Roman numerals to tell us what oxidation state it is compared to iron. Iron is a variable oxidation number, and therefore, but we need to calculate it, and therefore we have to use Roman numerals. Okay, so that's that one. The other one dealt with beaker drawings, and remember that the beaker drawings are simply a way to depict some type of ionic or even a non-covalent compound in solution, and we're talking about aqueous solutions. Okay, and so for strong electrolytes, okay, when we write these ions in solution, that's all we have. We show only the ions for whatever these compounds are starting off with. Now, what are these? Well, for example, a strong acid / base, or any soluble ionic compound. All those three means that they all dissociate 100% in an aqueous solution. Therefore, when we want to demonstrate a strong electrolyte or a strong acid or a strong base or an ionic compound that is defined as soluble in water, we show it with nothing but ions. That's it. And nothing is combined. They're all separated in their own separate charge. Weak electrolytes, what we do to demonstrate a weak electrolyte is we show at least one set of ions, because the weak electrolytes are materials that do not dissolve 100% in solution. So such things as weak acid, we gave you some weak acids, a weak base, or anything that is classified as insoluble based on the solubility rules. Now, even though it's classified as insoluble, and I have to get this because people have the impression, because it's labeled as classified as insoluble, that nothing goes in solution. That's not 100%. Insoluble just means that a very small number of that ionic compound dissociates. We still have some ions, and therefore that's why we say show it to be a weak electrolyte, or weak electrolyte, but only showing like one pair of ions that are in solution. Okay, and the rest of the material is still intact and not separated into their respective ions. It could be something like a small molecule like hydrofluoric acid, which is a weak acid, it's a liquid, and so it's in solution, or it could be a solid like magnesium hydroxide that is insoluble, and the bulk of the materials is solid, and we show it. We call those diagrams where the bottom of the beaker is a solid material kind of floating at the bottom of the beaker. Okay, and then non-electrolytes, all covalent compounds, with the exception of acids. Okay, acids like hydrochloric acid is a covalent compound, but due to the nature of the base, so to speak, as being an acid, it will dissociate. That's the only example of covalent compounds that dissociate. All other covalent compounds do not dissociate, therefore do not create ions, therefore are non-electrolytes, okay? Do not conduct electricity. And that's designated by the letters are NM, so covalent non-metal combination. Right, so that's basically it with respect to activities. Is there any question about that or about these? Okay. No. All right. Any questions in general? about the other chapters? If not, I'm going to jump and get into, hold on 1 second. Bear with me. I'm going to get into chapter 10. Now, chapter 10 deals with chemical reactions. We may have mentioned this, but of all the chemistry that's involved out there, we classify chemical reactions. And of all the chemicals that are out there in the world, there's only 6 types of chemical reactions. Okay, 6 types. Now, and we're going to go through each one. Now, but before we do that, we have to talk about conservation of matter. We mentioned this, in fact, in the beginning, in my first slide, I talked about, if you recall that thing with the grass, and we label a carbon atom and it went through the cycle. Okay, just to demonstrate what we're talking about, the conservation of matter. And it just simply states that we're not creating matter, nor we are destroying it. We're just moving things around, okay, creating new things. We do know that the total mass of reactants, if I start off with, 100,000 grams of reactants, when I'm done doing whatever I'm doing to that, I'm going to have 100,000 tons of product, okay? And it's an extreme example. I start with 10 grams product and reactants, I end up with 10 grams of products, okay? Excuse me. We can extend that by saying, if I start off with 10 million carbon atoms in the beginning with whatever I'm reacting, when I finish, I will have 10 million carbon atoms. And that's true for any atom, okay? Whatever I started off with, I'm going to end up with the same amount of those particular elements or atoms or whatever I'm working with. They're going to be in different forms, but nevertheless, they're still going to be there, okay? And that is conservation of matter. What this implies is we have what's called a balanced chemical reaction. Mother Nature must be happy, okay? And so we're going to start learning how to balance chemical reactions as we're talking about these reactions. Now, some of the chemical reactions, they're not very complicated as far as different entities reacting. So the balancing is kind of a trial and error. And we're putting numbers in there to balance reactions. It's a trial and error for some of these reactions. Other ones, we do have a little systematic approach, okay, which of course we're gonna give to you. But the other ones, if it's not the type of the type that we're going to talk about, then what you're basically going to do is just kind of do a little bit of trial and error. And looking at that reaction and do some, some analysis of what you're working with, all right? So what do we do? How do we handle this balancing chemical reactions? Now, we're at the point now, if we kind of regress here a little bit, is we started off, we talked about the elements, which are, behind me on my screen here, okay? Now, we haven't talked about every single element up there, there's 118, but we've talked about the major ones, which are the A group, okay? And we also talked about defining the properties of these elements, whether who's the metals, who's the non-metals. We talked about who gains electrons, who loses electrons. And then we even learned about, well, okay, if you're going to lose an electron, how many? And that was a function of where they were in the product table. And that was a function of trying to obtain that infamous octet, that happy 8 status. And you either lost electrons to get there, or you gain electrons to get to that 8. With the exception of hydrogen and helium, their number was 2, a duet, okay? So that produced the ions, okay? Then we took the ions and we started putting them together, the cation and the anion, to make compounds, okay? And then we started to learn how to name these compounds and how the anion name went from oxygen to oxide, okay? We talked about that. And now we're at the point where now we're going to take those compounds we made and react them with other compounds to make new products. All right, so we're at the point where we could be given a sentence or two describing a reaction, and based on our knowledge of these elements and the ions and things like if they're diatomic or they're metals or non-metals, and their physical state, whether they're solid, liquid, or gas, with that information, we're going to piecemeal a chemical reaction, okay? And that's what we're going to be doing. Once we do that, we're going to learn to balance it. Okay. So the first paragraph I just did is something we've been doing. We learned the ions. We got to put them together with an equal amount of protons, cations and anions, so they can cancel out. Okay. And then after we put those together, then we balance them, and then we put numbers in front. These numbers should not be confused with the subscripts. The subscripts are etched in stone. Once you put them together, you don't change those numbers. That is the ratio of the atoms with each other with respect to a compound. Water, H2O. That ratio is 2 hydrogens for every oxygen atom, okay? That's etched in stone. But the coefficient in front, we can change that any number of times. That tells us how many of those molecules or compounds we actually need. That's what that coefficient means. So, for example, let's take a look at this reaction. It's a very good reaction. It's well known. And well known in that if you take hydrogen gas and you light it up, you're going to have a big boom. Okay? This hydrogen gas, and notice I said hydrogen gas is diatomic. There's only 7 elements that are diatomic. So you may see it written as the reaction. This may be stated as, for example, the hydrogen gas in the presence of oxygen gas reacts to give you water, okay, vapor water, okay? We take that verbiage, that words, and convert it to a chemical reaction. We know that hydrogen gas is diatomic. Hydrogen atom is monatomic, but the term was gas. We also know that oxygen gas is also diatomic, okay? So if you forget that, well, that's going to be a big problem. You got to remember that those are diatomic gases and diatomic molecules, and we have to write the subscript too. React to give us H2O and water, so that's the formula, okay? This is a typical fuel used in rockets. And in fact, if you see rockets with a big old flume of smoke coming out of the exhaust, what you're seeing is a lot of water vapor coming out, a lot of force. So notice that we have a coefficient in front of hydrogen, which tells us that we have 4 hydrogens on the reactant side. Remember, the arrow is the reaction. To the left of the arrow are reactants. To the right of the arrow are products. So to the left of the arrow are 4 hydrogen atoms. We don't care about them being in whatever form they're in. We just know there's 4 of them total. On the product side, guess what? We also got 4 hydrogens in the form of water, H2O. There's 2 molecules of water. Okay, so that's a total of 4 hydrogens. Oxygen, we have 2 oxygens in the form of oxygen gas as reactant. And as a product, guess what? We have 2 oxygens in the form of H2O, water. It's still oxygen. Okay, we haven't lost any protons. We may have lost and gained some electrons here, but no protons. And so at this point, Mother Nature is happy because we have an equal number of protons, equal number of hydrogens on the left and right, equal number of oxygens on left and right. Another bit of information that you get once you balance that chemical reaction is the following, which is very important because we're going to use this information down the road here when we do calculations. That too tells me this. It tells me that I need 2 molecules of hydrogen gas. 2 molecules, you notice them here? There's 1 there, there's 2. For every 1 molecule of oxygen. And when that reaction proceeds, I end up with 2 molecules of H2O, okay? So that coefficient relative to of one reactant relative to another reactant is a ratio. And what I say about ratios, remember those ratios we were working with when we were doing the conversion of units? I said, remember how we do this? We're going to start using it, that technique of setting up the problems with the correct ratio and looking at your units. Well, here we're starting with that ratio, okay? And so what I have here is this. The relationship between the hydrogen and the oxygen is a 2-to-1. So I can set this ratio up as follows. 2 H2O per 1 oxygen. That's one ratio. Or I can invert it, where I got oxygens on top. Remember those conversion factors that we were doing? Okay, refresh your memory on those. Remember when we said one inch is equal to 2.54 centimeters? And I said at this point, you can have with centimeters in the top, with inches in the bottom numerator, or vice versa, 1 inch in the numerator and 2.54 centimeters in the bottom denominator, okay? And which one you use depended on the question asked. And normally the one you use has the units that you're looking for in the numerator. If the units I'm looking for is hydrogen, then I use this one on the left. If the units I'm looking for is oxygen, I use this one on the right, okay? And we'll come back to these, okay? But we're just looking at that relationship between the reactants. But remember this also, that there's a relationship between not only the reactants and themselves, but the reactants and products. So from hydrogen to oxygen, guess what? It's a 2-to-2, and that also is a ratio. So 2 hydrogens to 2 oxygens, or written as 2 oxygens over 2 hydrogens, okay? Obviously the 2's cancel, and you can see, if you see that, it could be 1-to-1. That's okay, that's correct. But if you don't see it, leave that 2 in there until you're comfortable with it, and then you recognize it's a 1-to-1. If it's a 2-to-2, 3-to-3, 4-to-4, 1 million to 1 million, that ratio is still 1-to-1, okay? So that's the ratio between hydrogen and water. Yes, and also we got one more ratio, and that is between oxygen and water, okay? Which means I got 1 oxygen over 2 H2O, or 2 H2O over 1 oxygen. So for this simple reaction, we have 6 ratios that relate the reactants with themselves, the reactants and the products. And these ratios we would utilize when we start doing calculations, okay? And so that's why it's important that we balance the chemical reaction correctly. But you can see here that if we don't balance it correctly and we use the wrong ratio, our numbers are out in left field someplace, all right? If we don't balance this, if we left this 2 out and just said 1, then that ratio would be a 1-to-1, which would be incorrect. All right. So balancing is crucial. Very, very crucial when we get ready to do our calculations. So for these type of simple equations, we're going to do a real. It is a trial and error at this point in the beginning. And so basically we put a number, a coefficient, either on the product side or the reactant side. But normally we're going back and forth until we're at the point where everybody's balanced, okay? So we may start in the reactant side, and that increases the amount for one element. So we go to the product side, put a number there to get that one in order, and then that may increase it another one. So we go back and forth until everybody's happy. So let's take a look at this here. All right, so we got N2, which is nitrogen, and H2, which is hydrogen, and this NH3 is the infamous ammonia. So it could read Nitrogen in the presence of hydrogen reacts to give ammonia. See, that could be put that in words, and then we can take those words and then decipher the words and put them into this reaction. Okay, so N2 plus H2 react to give us ammonia in the gas form. So we got to balance this. And so, you can attack this in multiple ways. One way is no better than the other, So, one way I see here is this. I see that I got 3 hydrogens sitting over here, and I got 2 hydrogens over here. Now, if I think about this, isn't that reminiscent of some other disparity that we were working with earlier? Remember those examples of compounds we were trying to make where you had a +2 and then you had a -3, and we were looking for a common number. Okay, and so I got 2 here, 2 in the reactant side, 3 in the product side. Can you see that if I'm looking for a common number, which in this case would be 6, right? So if I put a 3 in front of hydrogen, that gives me 6 hydrogens. And if I put a 2 in front of ammonia, that gives me 6 hydrogens. So with respect to hydrogens, I am happy here. It's balanced. 6 hydrogens. The hydrogens are balanced. Now, in the process of putting the 2 here, what that did was kick up my nitrogens, right, to 2. So now I got to go check. Do I have 2 nitrogens in the reactant side? Lo and behold, yes, I do. I got 2 hydrogens. And so I have a balanced chemical reaction by simply putting a 2 in front of ammonia. Okay. And it gives me a ratio of nitrogen to ammonia of 1:3. So always when you balance them, always keep in mind, I have this combination now. I can write this ratio. You might ask, well, I don't understand. What's the deal with the ratio? Okay, let me do an example like we did with the units. What if the question says, if I have 60, let me go over here, 60 hydrogens, how many nitrogens do I need? Okay, remember those questions we did? It says we write down what we're given. I got 60 H2, right? And the question is, how many hydrogens do I need? So my final units will be in nitrogen, right? So hydrogens here, what does that tell you? It tells me that hydrogens must be in the denominator. Why? Because I want them to cancel, just like we did the conversion factors. And that nitrogen's on top. Okay, so guess what? I'm using this one here. So I got one nitrogen over 3. This comes the mole. This will give you a name for it. It's called the mole ratio. This comes from the balance chemical reaction. And that's why it is so important that we balance it correctly. And so it's a 1:3 ratio. So what this means that if I start off with 60 hydrogens, I require 20 nitrogen molecules. Okay. Isn't that 60 to 20? Isn't that a 3-to-1 ratio or 1-to-3 ratio, whichever way you look at it? It certainly is. See, there's a 1 here. Okay. I could have said 120 up here, and that would have been 40. My ratios are 1-to-3. All right, so that's how this ratio business works, okay? That's how we do it, because what happens, for example, in, quote, the real world, as they say, is, this reaction could be done mass-produced in like tons of it. You can be working in an ammonia factory trying to make tons of this stuff. And so you say, all right, I want to make 100 tons of ammonia. Well, using that information, you're using the same equation here, you can calculate how much nitrogen you need and how much hydrogen you need to make 100 tons of ammonia. And ammonia is very crucial for multiple things, things like fertilizer and so forth. Okay, so that balanced chemical equation is true whether I work in the lab with small quantities or I'm in an industrial park someplace making tons of this material. All right, let's do one more. We have here hydrogen gas in the presence of bromine liquid reacts to give us hydrogen bromide. Okay. Well, to balance it, we can simply put a 2 in front of HBr, and that balances everything, right? You got 2 hydrogens as product, 2 hydrogens as reactant, 2 bromines. I'm going to call them BRs because one's bromine, the other one's bromide. 2 BRs as reactant and 2 BRs as product. Okay, so that was a pretty straightforward balance. Here we have carbon monoxide in the presence of oxygen reacts to give us carbon dioxide. So we can put a 2 in carbon dioxide. Okay, that kicks up the 2 carbons and it gives me 4 oxygens. And so by simply putting a 2 in front of carbon monoxide, all right, that gives me a total of 2 carbons and 4 oxygens on both sides of the equation. Okay, so that's some real simple chemical reactions that need to be balanced. Unfortunately, there isn't a little technique for these types, but essentially just use coefficients and basically ends up to a trial and error. Now, if, for example, you do that and you end up with these numbers, maybe you end up with 4, 2, and 2. Okay, it is a balanced chemical equation. It really is. Okay, but when you come up with your numbers, see if you can reduce them to the lowest numbers. Now, all these numbers, 2, 2, and 4, I can reduce because they're divisible by 2. All right, and that by doing that, that gets me to that. So always use the coefficients at the lowest numbers that you can use. Okay, kind of bring it to its lowest terms. That's how they say that in mathematics. Recall the physical states. We had solid, L for liquid, G for gas, and then aqueous solutions put in water, are AQ. Okay. Now go back and refresh your memory with respect to the elements. Which ones are solid? Which ones are liquid? Which ones are gas? And there was a slide that showed all that. There's 118 elements, 2 of them are liquids, 12 are gas, and the rest were solids, okay? Remember which elements are diatomic. Have no fear of ice cold beverage. Okay? Those are diatomic because you need to write them correctly with a subscript 2. Okay? And as we stated, the subscript tells how many atoms for that particular molecule, whereas the coefficient tells us how many molecules we have. Okay. All right. Well, here's our first reaction. We're going to take these words and break it down to an equation. Okay. Keeping in mind this information we just talked about. Which ones are solids, which ones are diatomic, which ones are liquids, which ones are gases, etc. Because we want to put the physical states. So we have here, sodium reacts with chlorine to produce solid sodium chloride. Okay, a couple of key words to make note of. Sodium. That's all they're saying, simply sodium. They're not saying sodium whatever, just saying sodium. So that obviously indicates that it is an element. So we can very quickly write sodium as one of the reactants, okay? Now, how do we know what is reactants and what is products? A lot of the keywords that represent the arrow are things like to produce, okay? To produce is the indication of the arrow, or it could be react with or make or anything of the term, any kind of word that suggests that whatever I talked about before, something happens to them then to make whatever the products are. So to produce in this case is indicative of the arrow, okay? So sodium reacts with is telling you there's another species as a plus with chlorine. Now, we know that chlorine is diatomic. Have no fear of ice cold beverage. No, it's not chloride. It is chlorine. We're talking about the element chlorine, okay? Then they tell you to produce is the arrow, solid, so they're giving you the physical state of the product. And then we got the final product, sodium chloride, which is an ionic compound, metal and non-metal. Now, before we write the formula, like we've been doing before, we write the ion first. Sodium we know is in group 1, group 1A. It is a metal. It will lose electrons, so it results in a +1 charge. Chloride, okay, that's why hopefully you can see the difference, how to distinguish the element and the ion. Chloride is the ion. Chlorine is the element. So chloride, we have to go to chlorine to figure out where it's in the product table. It's in group 7. To become ionic, it would gain 1 electron because to get that magic weight. So therefore we have the ion of negative. Okay. Now we know the charges. We know we're going to put in enough of each so they cancel out to give 0. So in this case, it's simple +1 and -1. We have the formula NaCl, and it's a solid in the physical state. Okay. Sodium, we know it's a solid, one of the metals, and we know that chlorine is a gas. Okay. So at this point, we have written the base formula. Okay. Now the next step is we need to check to make sure it is balanced. And as a little kind of a guideline is if you see an element all by itself sitting there, just leave it alone. Let it hang out there, because generally at the end, you may need to put a coefficient there to help things out. So leave that alone, work on the other reactant. In this case, chlorine has 2 of them. There's 2 Cls. So what we do is, check this out. We put a 2 right in front of sodium chloride. That balances out the Cls, okay? But it kicked up the number of sodiums, which means we go back to the sodiums and we put a 2 in front of it, okay? Now we go back and do a check. We got 2 sodiums on the left, 2 on the right, 2 Cls on the left, 2 Cls on the right. Mother Nature is happy, okay? In this particular reaction, which is, I mean, it's fascinating in itself. Why? Because you have a metal, sodium metal, that is so reactive, we have to store it in oil. You leave it out here, it can react very readily with moisture in the air. And when it reacts with water, it's a violent reaction. It generates a lot of heat, generates hydrogen gas, and high heat, hydrogen gas goes boom, okay? Very reactive, hazardous solid. Chlorine is a gas. More specifically, it's a poisonous gas. So we got a reactive metal, a poisonous gas. They interact with each other. 2 electrons are transferred from the sodium to the chlorines to make chlorides. And that transfer of those little tiny electrons results in a product that you can now put on your French fries or your food and not hurt you. Unless you got high blood pressure, and then you don't want to deal with the soda too much. Okay. So that's what fascinated me about chemistry in general, that this little crazy electron can have such a effect on the whole compound. Amazing. Anyway, that's my breakdown of the process. Now let's clean it up a little bit so you can see it in their setup. So we got the first step is to write down the elements that we were given based on the words. Okay. Then we added the physical states based on our knowledge of, solid, liquid, gas. And so if it's an aqueous solution, they definitely will tell you. It will tell you aqueous, so you can use AQ if this was aqueous. We know that you were saying if chlorine is diatomic, why don't we write it as NaCl2? Well, the whole thing is crazy, for example. Why? Because what does this mean, this formula right here? Okay, this means that implies that sodium must have a +2. Why? Because each chloride is a -1, right? And that implies that sodium is a +1, and it can't be. Why? Because again, sodium's in group 1. And so this formula is just totally out of whack. The other thing too is this: you see sodium chloride written like this, and you think, oh, okay, this is diatomic chlorine. However, there's sodium in there. Okay, so it's a compound. Unfortunately, it's the wrong compound. It's not a 2 there. It's a 1. But don't just because you see a diatomic here, don't assume that carries over. Okay. It doesn't. That diatomic element does break up into making ions. All right. And there's a balanced chemical equation. Here's another one. Just break it down. Aluminum reacts with bromine to produce, there's another word, to produce. Notice the previous word was, what was it? To produce, there was another one, yields or reacts with. Okay, it must be down the road. To produce, so we have aluminum reacts with, so this react to me is a plus, and then we got bromines in here. To produce to me is an arrow, the reaction arrow, solid aluminum bromide. Okay, so let's write down. Aluminum, we know, is a solid. Okay, it's a metal and it's a solid. It's in group 3. 3A. It reacts, so like I stated, reacts to me as a plus with bromine, just like chlorine earlier. This is the diatomic Br2. To produce is our reaction arrow. And then they say solid aluminum bromide. So here's where we put them into ionic form. Aluminum is in group 3. So it ends up with a +3 charge. Bromine is in group 7. It has a -1 charge, just like chloride did. Okay. We need 3 of them, 3 of the bromides to cancel out the +3 of aluminum. Therefore, our formula for aluminum bromide is AlBr subscript 3. And we know it's a solid, so we can put S in parentheses. Okay. All right, now we got to balance it. Now, notice the disparity in numbers. I'm going to leave, here's the element by itself, my monatomic element. Just leave it alone. We'll come back to it, okay? Let that be the last thing you balance, or add a coefficient if you need. So we got bromine 3 on the product side and 2 on the reactant side. Again, we have dissimilar numbers. Okay, we look for a common number, again, which is 6. So we can put 3 in front of the bromine and 2 in front of aluminum bromide. What that does, it balances out our BRs. We got 6 on the left, 6 on the right. BRs are happy, but it did kick up our aluminum to 2. So we simply go to aluminum and add a 2 there. Okay. And now double check yourself. We got everything's fine. We got the physical states. It's good. Okay, it's balanced. So let's take a look at their the one that's not as messy. So we had the states and then we got balance it at the end. And there we go. We have a balanced chemical reaction. Note the ratio. Okay. I have 2 aluminums over 3 BRs. I can write it like that. Or I can write it with 3 BRs on top. There are 2 aluminums in the bottom. Okay. And that's our ratio between reactants. And between aluminum and aluminum bromide, it's a 2-to-2 or 1-to-1. And between the bromine and aluminum bromide, it's 3-to-2. Okay. You know, so like I said, be aware of the ratio. Okay, might as well get used to it now because it'll be coming as far as our calculations are concerned. All right. Here's that ratio I just spoke about between the aluminum and bromine. Don't disregard the other ratio, okay? Because remember, for this little equation here, you got a total of 6 possible ratios. All right. Now, up to now, we've been writing using ionic compounds, creating ionic compounds, right? All right, now here, not quite. It says, write the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. It sounds like a covalent compound, right? Yes, it does. All right, so we got the reaction of phosphorus reacting with, to me that's a plus, with oxygen. Oxygen's diatomic, okay? Phosphorus is P. To make, here's another variation of the word react with, but to make, to me, is the arrow. And then we got diphosphorus pentoxide. As we were doing ionic molecular compounds in writing and name, either naming or writing the formula, here we're writing the formula, write the parent formula first, phosphorus and oxide, okay? And then put in the prefixes. So we got di, which is 2, and penta, which is 5. And this is solid because they're telling us they're solid, okay? And so here we are, we got everything all set up. Now it's a matter of writing it. So we got phosphorus, P, that's a solid, okay? Plus oxygen, diatomic, that's a gas, reacts to make diphosphorus pentoxide, which is a solid, and that's given to you. So there. Based on the wording, we've written the reaction, okay? Now, we have to balance it. Okay. As the previous example, we had a disparity of 2 to 3. Here we have a disparity of 2 to 5. Okay, no, remember, here's the element, the monatomic element, leave it alone. So work on the oxygen. Okay, so we got 5 over here, 2 over here. We need a common number, which is 10. So what if we put a 5 right here? Okay, that gives us 10 oxygens. And if we put a 2 right here, guess what? That gives us 10 oxygens in product side. So the oxygens are good. which means then that we got 4 phosphorus on the product side, which means we got to go back to the reactant side and stick a 4 right there. All right, so go back and double check, 4 phosphorus, 10 oxygen, 10 oxygen, we're balanced. And everybody's happy. Okay, so let's clean it up and let the type words come down. So here's the formula. Here's a physical state, okay? And here's the balance. And so, you know, we've balanced it, and now look, keep note of my ratios, okay? 4 phosphorus over 5 oxygens. 4, 5 oxygens over 4 phosphorus. All right, well, let me ask you a question. Using the ratio between phosphorus and oxygen, if I have 20 oxygens, the question is, how many phosphorus do I need? Okay. Question number 1 would be, okay, which ratio would I use? Left or right? Now, no need to guess. Okay. But what do we do like we did before? We write down what we're given. So we're given 20 O2s, right? That means we're going to need a conversion factor with O2 in the denominator and phosphorus on top, right? Because we want the O2 to cancel out. So what does that mean? Based on the balanced chemical equation, the phosphorus to oxygen ratio, there's 4 to 5 ratio. Okay, and so now unit-wise, I'm left with phosphorus. So if I start off with 20 O2s, and you see that I need 16 phosphorus, does that look correct? My number look good? Yeah. And the ratio between 16 and 20, isn't that 4 to 5? Yeah. I could have doubled that, 32 to 40. Guess what? It's the same ratio. All right. So that's how we use the ratio once we balance a chemical reaction. We will eventually set up 3 conversion factors on average to get to whatever answer we're looking at. And so a lot of it is important that we know the stoichiometric relationship between, we call it stoichiometry, and that is simply the ratio between the reactants. We were doing bicycles earlier last time, you know, when I said the bicycle, it has 2 tires to the frame. That is a stoichiometric relationship. 2 tires to 1 frame. A tricycle, its ratio will be 3 to 2. A car, its ratio to frame and tires will be 1 to 4. Okay, that is what we call it. We have a whole chapter on stoichiometry. All right, let's, and it sounds complicated, but it really isn't when you think about it. Just looking at the ratio, how many of each I need for it to properly react. Now, and that ratio holds true, that 4 to 5 right there holds true, again, whether we do it in the lab scale with a few milligrams, or we do it out in the construction, a chemical plant where you're making tons of it. Same ratio applies. All right. Now, here is a challenging problem. And I always advocate that whenever you have something that's very difficult, break it down to the steps, break it down to pieces, okay? A lot of times, Chinese have a proverb about a long trip begins with, a step at a time, something to that effect, to paraphrase it. And it's true for multiple things, okay? When I first started my education 100 years ago, I'm looking at where I want to be, and it looked like it was going to be 100 years from now. And the thing is, when I stopped thinking about 100 years from now to get that piece of paper and only work with what we're going to do today and tomorrow. And then the same thing over and over again. Before I knew it, I was at the end of the road and I was there where I wanted to be, you know, and not focus on too much and way down the road because that put up a lot of stress and, you know, didn't need that. So break this problem down stepwise and I guarantee you'll solve it. And I'm gonna talk you through it here, okay? What they're doing is, in fact, this is another example of another chemical reaction that we will talk about. It's called a double displacement reaction, but we'll just first break it down. It says here, write down and balance this aqueous reaction, okay? It says nickel, Roman numeral 3 sulfate, plus lead, Roman numeral 2 nitrate, produce nickel 3 nitrate and solid lead 2 sulfate, okay? Obviously, we have ionic compounds. So what we need to do is to first break it down. And so I'm going to color code this, and the first one, what color do I have? This blue. Okay, so let's write these into ions first. So nickel 3, doesn't that tell us that we are working with Ni plus 3? Right? Remember that? Roman numeral applies to the metal. Sulfate, okay? ATE, not IDE, but ATE should direct you to the periodic table under the polyatomic ions. And you'll find that there's sulfur in the ATE deals with oxygen bonded to sulfur, and it's a polyatomic ion, specifically 4 oxygens. And so we have SO4, and it has a -2 charge. Okay. All right, let's do the next one. Plus means that's the other reactant. So we're going to deal with lead 2 nitrate. All right, so plus is this. Lead 2 nitrate, which is Pb plus 2. Okay. And the nitrate, then again, go to the polyatomic ion table, and you'll find that nitrate is NO3 negative. Okay, so we wrote the ions. Again, you have the name of the compound before you put anything together, and specifically ionic compounds. Write the ions, because you want to make sure you put them together with the correct number of anions and cations. All right, next one would be, let's do this color. Produces, obviously we got an arrow here, okay, nickel 3 nitrate. So we're still working with nickel 3, which is Ni plus 3, and then we're still working with the nitrate, okay, so that's NO3 -1, okay. Now, I should have been adding the numbers here, but now let's continue. Let's do the next one is lead 2 sulfate. And not only that, they're telling you it's a solid, okay? And so we're still working with lead 2 sulfate. And that's SO4 -2. Okay. Notice what's happened here. The nickel is partnered up with the sulfate, but when on the product side, nickel now is partnered up with the nitrate. The lead begins with the nitrate, and then at the end, it ends up with the sulfate, okay? So in essence, the anions and the cations have exchanged partners. And what drives this reaction is the solubility table. Remember this, solubility table. This is a DD reaction, double displacement reaction. What drives that is solubility. If we look at the products and we look up the solubility, you will find that lead sulfate is insoluble. And that's why it's a solid up here given to you. If you look up nickel nitrate, you'll see the nitrates in the left column of the soluble table. Anything bonded to nitrates is soluble. So that is aqueous. And also, we're in an aqueous condition. All right, now, aqueous solution. What we got to do is put these together in the formula so we can put them up there. Now, notice here we got nickel 3 and sulfate as a 2. We have a disparity in charges, but like we've done before, we just use a common factor. And so we're going to need what? 2 nickels and 3 sulfates. So the formula for nickel sulfate, nickel 3 sulfate, is simply Ni2 parentheses, because we need 3 of them, sulfates, 3 sulfates. Okay, so that is nickel 3 sulfate. All right, now we're going to put together the lead and the nitrate. You can see the nitrates are -1, so we need 2 of them. So it's simply PB parentheses NO3 2. We need 2 of the nitrates to balance out the +2 of the lead. Produces nickel 3 nitrate. Nothing's happened to it. We've still got nickel 3, began nickel 3, it ends nickel 3. But now we have 3 nitrates. So we got Ni parentheses NO3 and parentheses 3, because we need 3 of the nitrates for every nickel +3. Okay. And then the last one is lead ion and the sulfate. They're both +2, negative. They're both, I have a 2 magnitude, +2, -2. So we can simply put them together as a 1-to-1. And we know that this is a solid. All right. Everybody else is aqueous. AQ, and so is the nickel 2 nitrate. Okay. In fact, for this type of reaction, nickel plate, you have the 2 reactants that are soluble in water, and normally they're clear solutions. And when you put them together, it precipitates. And it precipitates because the lead sulfate is not soluble. It's classified as insoluble in water. You form a solid. Okay. Yes, there's a little bit of ions in solution. Remember that. But the bulk of it is a solid, and down at the bottom of the test tube, if you got it in a test tube or beaker. Okay, ladies and gentlemen, we got the formulas together, put together properly with the correct number of ions for each one. Once that's done, we got the physical states set in. Now we got to balance it. Now, here's the deal for double displacement reactions. Follow the polyatomic ions. Now, these are the guys in parentheses. Now, you don't need to break them up and say, oh, I got 12 sulfurs and 14 oxygens. No, just count the number of units within the parentheses. So you can see on the left side, we have 3 sulfates, right? But on the right side, we only got 1 sulfate, okay? On the left side, we got 2 nitrates. On the right side, we got 3 nitrates. So we can do the dissimilar disparity there. It's a 3-to-2 ratio. So what happens if I put a 3 here and a 2 right here? Wow, what that does, that gives me 6 nitrates on the left-hand side and 6 on the right-hand side. So my nitrates are happy. their nitrates are done, looks like, right? It made my nickels go up to 2, but guess what? Already the nickels are taken care of because there's 2 nickels there to begin with. So my nickels are okay. Now, but by putting a 3 in front of lead nitrate, it kicked up my lead to 3. So I got to come over here to the far right and put a 3 here to kick up my nitrate, but that also kicks up my sulfate to 3. But that's okay because my sulfate's already at 3. And so bottom line is, guess what? You are balanced. So again, when it comes to polyatomic ions, you want to balance them, I stated that wrong. When it comes to double displacement reactions, you balance them, follow the polyatomic ions, okay? Keep track of those as one unit and balance those first, and everything else comes into, by default, will balance itself, okay? So here you can see it looks like a pretty complicated reaction, and it really is. But what we did is we first broke it down. We first broke it down by first breaking down the ions that we had. Once we did that, we knew how many of each of the polyatomic ions and how many of the other ions we need to write the formula. And that's why we wrote the formula there, the whole thing. Once we got the formulas written correctly, then we balanced it and we followed the polyatomic ions. And we went back and forth. That's what balancing is about. You may start at the reactant site, then move to the product side, and maybe even go back to the reactant site, back and forth, okay? Whatever it takes to get all the atoms balanced out. Okay. All right, so this is pretty big reaction, but it really isn't when you think about it, okay? Because it's just a matter of those ions and putting them together properly in the right number of each. And that's what we ended up with right there. And the ratio is still the same. See, the ratio is a 1:3 between the nickel sulfate and the lead sulfate. That stoichiometric relationship now we can utilize if we need to do any type of calculations. Okay. You know what? I may stop it here because I got 12:25. Why don't I stop it here on slide? We'll start on slide 11. What this does is describe the 6 types of chemical reactions, okay? You already been exposed to one of them, actually 2 if you think about it, is the acid-base reaction, the neutralization reaction. That is one type of reaction. The other one, like I mentioned, is a combustion reaction. Anytime you combust what we're going to combust is a hydrocarbon. Hydrocarbon is any compound that simply has nothing more than carbon and hydrogen. That's a hydrocarbon, okay? And then we got 4 more to work with. The last one I just showed you, that's a double displacement reaction. So of the 6, you've been introduced to at least 3 of them, okay? All right, well, we'll get in more detail, and what this slide does is break down those equations in general terms. In general terms, they give you a little more latitude so you can recognize it and then hopefully pick out any reaction you're given and be able to describe what type of reaction it is, okay? And I will go to each one to help you identify what makes it that particular type. Okay.